what it is allocating, right? It has to keep track of some table. So it has to have some table which says that, this 10 bytes allocated, it's been allocated, this has been allocated, it's been allocated, this has not been allocated. So it has to have some data structures to figure out what is free and what is not free, right? This is inside kernel anywhere. Like if you have resources, they have to be managed somehow, right? You have to keep count of how many resources are there, who has them, so when I get it back, I know I can manage this stuff, right? So C, instead of managing it like a table like this, it manages it the following way. If you ask for 10 bytes, right, he'll give you 10 bytes. He'll store the next free block address immediately following this, right? So the next address points to the free block, and in this case, the rest of the stuff, right? So it keeps a pointer there, right? Yeah.
So how does it know it's the end of your data and it's the beginning of the pointer to the next free block?
I'm sorry?
How do you know when your data is done if it starts looking for the pointer to the next free block?
Oh, so it can have other stuff. You can have the count or whatever, right? But it keeps all the structures it wants right next to the stuff. The first byte is the pointer. Then you can keep the amount of size or whatever, right? Okay. Whatever it wants, you can keep it here. It doesn't maintain a separate structure. It maintains it right here, right? And it's free to do whatever it wants, right? Because you're assumed that when you ask for 10 bytes, you only write 10 bytes. You're not allowed to write 11 bytes, right? So if you wrote something here, that's your fault, right? So essentially, this is what it does, right? It keeps going around like this. So if you ever wrote a code where you say pointer of 11 equals 0, right? Allocate 10 bytes and accessing the 11th byte. What happens?
It overwrites the 11th space to the right of your pointer.
Yeah.
It doesn't really matter what's there beforehand.
Yeah, you're fine when you're writing it, but now you destroy the whole malloc library, right? It is going through chaining like this. So now you wrote something into the pointer, and you'll be fine. You'll keep progressing, right? One of the ways when you fail is when you do another malloc or when you do another free, right? When you do a malloc, it chases these pointers. It tries to go through these pointers to figure out, to give you, find the next free space, right? So your malloc library goes here, finds this pointer, jumps there, and finds there, and keeps going, right? So if you overwrote that byte, then it'll fail. Or if you're trying to free something, it has to go through and figure out what pointers to manipulate, and they fail. So this is why when you mess something with malloc, you actually crash much later on when it tries to do malloc. How many of you have seen this case where your program says it crashed on malloc or free, right? Few of you, right? So once you start writing these programs, you get these weird errors way away from where things are, right? This is considered to be a good thing, right? Because as we'll see later, it's very hard to provide protection on a very small boundary, right? Operating system can prevent this by saying you're not allowed to write anything beyond this using protection mechanisms, which we'll see in the next module, right? But those all have overhead, because anytime you have to call the operating system, it's expensive, right? So the people who designed malloc figured, if you mess up anything with malloc, right, you will know about it because you will always corrupt something. Because if you didn't do that, then you won't know. Because if it was some data, then you're modifying something and you can keep going, right? And so there are some libraries which actually write some good values here, so it checks. So you can compile your program with debugging malloc libraries, which essentially do some sanity check every time it leaves. But the regular malloc does not do that, so you get a crash over there, right? So I'm not sure how many of you learned that from your programming language or architecture class, but the assumptions when you talk about it in the book in terms of processes and stuff, kind of assume that you know that, right? Did you guys go through that in your programming language class? Okay. So anyway, so it's good to know. I mean, I think a lot of people get frustrated with C because it seems to do something strange. That's because you don't know what it's doing, so it looks strange, right? So getting back to the chapter, right? So essentially you're trying to first figure out how to give resources, and we start with the resource CPU because we consider that to be important, right? In order to do that, first the OS has to know who it's talking to. It needs to know something about you meaning this abstract sense, right? So it has to have this entity where it can give it CPU, disk, or what have you, right? And it can take resources, right? So it needs a representation of you, and you here means the program that you want to run, right? So the name for this thing is the process, right? Essentially, process is the way for the OS to know that you exist, right? And process is associated with the program because that's what you're trying to run. So if you try to run MS Word, the OS first creates something called a process, right? So it can refer to the stuff, and then it'll load whatever, and it'll act like Word, right? So that's the notion of process. So the definition is it's a program in execution, right? The program is not running. If it's on the CD, then the OS does not care. But once you start to run it, it has to know about it, and the data structure it keeps is the process. So once it has to know about you, it has to know everything about you. It has to know all the stuff that it can have, right? So it has to know what are the programs. So in this case, there's a notion of stack, there's a notion of heap, right? And there are other data structures that it keeps track of. For example, there is text, right? Text is where all your program code goes, right? It's still memory, but it treats it slightly different. It can treat it slightly different. And it has data and all those things. So it creates all this stuff, and it has to know where your stack is, where your heap is, where your whatever you asked for. It has to keep track of all the devices. It keeps track of everything inside this notion of a process, right? It also keeps track of the program counter, which tells you what exact precise instruction you're running at that point, right? And we'll see that how that affects in a couple of slides. So process goes through these different states, right? So when you first start this program, the process is created in a state called new, right? Essentially, it just starts what it required. It has not given any resources for it, right? And at some point, it moves it from the new state to the ready state, right? And the decision to when to move it from the new to ready state is dependent on the long-term scheduler, right? If it sees too many processes, then it can decide, I'm not going to take any more. So the long-term scheduler decides whether you want to come into the system at all, right? But once you go into the ready state, right, you're ready means that you are all set to go, but you don't have some resource, right? And the resource that we are worried about here is the processor, right? So if you don't have a processor, you wait in the ready queue, right? And then it decides when it has the processor, who should get the thing. So you can potentially have lots of processors waiting on the ready state, and it decides who should run using different scheduling algorithms. And those are the short-term scheduling algorithms, right? So there are a bunch of processors which are all set to go, and all they're waiting for is a CPU, and the OS figures out who should run next. And running state is the case where you have the CPU, you have all the resources, you can make progress, right? And if you're in a single processor machine, you can only have one process which is running. If you're in more processors, right? If you have 4 processors, then you can have potentially up to 4 different processors running, right? And whenever you have to make an I/O request or something, you go into a wait queue, right? So if you're requesting for some hard disk or something, you can't proceed even if you have the CPU, so you put in a different queue, right? And when you finish your I/O, you go back to the ready queue, and then you keep running. So you go through this cycle. You keep running, and when you need some I/O, hard disk, terminal, mouse, or whatever, you go into the device wait state, and from there you go back to the ready state, and then when you get the CPU, you make progress, right? And when you're eventually done with all your computation, you exit the system, right? And the data structure where the OS puts all this stuff is called the process control block, right? I think Linux calls it task control block. Essentially, it's one big data structure which has everything you need to know about a running process, right? It has a process state, it has a program counter state, CPU register, memory management. anything you can think of, you put into the stuff, right? And it's a fairly big structure. So if you, I'll try to show you some code examples from Linux, but essentially it's a very large structure. It's like 4 or 5 kilobytes, right? It has to have all the structure because that represents the process, right? So from this point on, OS only, when it thinks of a process, it thinks of a PCB, right? And it gets passed around different places, but it has all the information it needs, right? So why we need PCBs? At the beginning of the class, I talked about multi-programming. Running different programs to make it look like you're running more than one at the same time, right? Which means that you may have to switch from one process to another one. So let's see. So the assumption here is there are 2 processes. They are both in the ready state, right? Meaning that they can both make progress. If you give the CPU, they can both run, right? So in this context, and you don't want to give the process, to process 0 and let it finish, because that means the other one is starving. It doesn't get any of this stuff. So what you want to do is you want to keep them both busy to make it look like you're doing good stuff, right? So what you do is you let P0 run for a while, and then you kind of magically make like this run go for a while, and then you make this go for a while, right? So during this times P0 is running, and during this time P1 is running, right? So both P0 and P1 feel like they're making progress, albeit slowly, right? I mean, they're not going as fast as they could, but they're still making progress, right? So when you do this, this is called a context switch. You're switching a context from this process to this process, right? Which means that the OS has to figure out that the PCB for this should change its state from running to ready, and the PCB for this should go from ready to running, right? Which means that it has to save all the stuff it remembered here into the PCB and restore everything that it wanted from here, right? And some other things are registers and other temporary stuff that are inside the machine. So when it does a context switch, it stores all the state, stack pointer, program counter, register values and stuff into the PCB, right? It restores all the values which were from the PCB onto the current machine and lets it go, right? By doing this, this program can never know that it was not making progress here, right? Unless you can look at time, this process has no idea that it was switched out, right? And that's a facility that comes from the hardware, right? The hardware has to give some facility to say, I load all these values and then I let it go, and it keeps going, right? It doesn't know that it was frozen at this point. So you could think of storing all the state as the freezing part and the restoring part as the unthawing part, right? So that's kind of what this graph shows, right? So P0 was making progress. At some point, it has to save all the state into its program control block, restore all the values from the other program control block, and do the hardware trick to say go, right? It keeps running. At some point, it decides to give the stuff back, and then other one makes progress, right? These are not trivial tasks. I mean, you have to store a whole bunch of state depending on the hardware. It depends on the hardware, right? So the hardware has lots of state. I'm not going to go through all the details about how complicated the hardware can be, but if you take a hardware class, right, that's one of the things you worry about. Depending on the number of registers, number of pipeline stages, and all those things you talk about, everything has to be clean, because once you go into the state where PCB1 is running, right, you cannot leave anything from PCB0, right? Because it's a security violation, right? So if you're calculating the grades for the class, right, when I run a new process, the process has no idea that something else was running and left some data. So you have to clean everything, scrub everything, and load everything, and restore everything, right? So you don't want to do this too often. So one of the things you want to do is, if you keep doing this very often, you're paying this cost so much that you're not making good progress, right? And that's the stuff I want you to try for the homework project 1, right? Essentially, you're changing what is called a timer. Essentially, on a normal machine, the hertz value that you set decides how often you do the switching, right? To give you a good feeling, right? So when you try with the 10 hertz, that means every 100 millisecond, 1 over 10 second is 100 millisecond. Every 100 millisecond, I'll do this switching, right? If you set 1000 hertz, every 10 millisecond, you'll do a switch. Every 1 millisecond, sorry. 1 millisecond, you'll do a switch, right? So every 1 millisecond, I will do the part where I save the PCB 0, load the PCB 1, and let you make progress. And then you do this, keep doing that, right? So that's overhead, right? Anything that OS does is useless work. You don't really care. You want your program to run, not this component, right? So depending on your particular application, you will notice that going to 1000 hertz will make it look faster, but you're wasting all your time trying to do the switching, right? And that's what I want you to try when you do the homework project, right? Yeah, one thing to remember is anything that OS does is overhead, right? We can talk about it being smart and all those things, but when you buy a Word, when you buy a PowerPoint, you want the PowerPoint to be running all the time. You want it to be doing stuff for you, not give anything to CPU because to the OS, because that's just a waste, right? So you want to avoid those stuff. You can't really avoid it, but you can avoid it by not doing this often, right? So whenever you switch this process, remember the PCB defines who the process is. So depending on what state it is, you can put them in a different queue. So the OS maintains lots of queues inside, for the different device drivers and disks and stuff. So when a process is in the ready state, right, and it's being yanked and something else is moved, you put it back on the ready queue, right? If it has to make an I/O request on a terminal, you put it on the terminal queue. If it has to make an I/O request on the mouse, you put it on the mouse queue. If you have to, and so on, right? So it has to have lots of these queues, right? And then it moves this stuff back and forth. So essentially, when you have multiple processes, it yanks one of them, puts them in some queue, puts something else in another queue, makes them run, and so on, right? And that's the magic of the OS. That's what we're trying to figure out, right? And how it does that is the scheduling process, right? So if it does that in such a fashion that all the stuff that you really care about gets to run, then you're happy. Otherwise, you're not happy, right? So the trick is, how do you do this juggling? Yes?
Is there some way to account for trying to put a process on multiple queues? Some programs wait for either keyboard or mouse input. How would it handle that?
In the one Neumann architecture, so the question is, can you wait on two simultaneously, right? You can't. You only wait for one, right? This is part of the von Neumann architecture, whatever, where you have multiple instructions, right? You operate on them sequentially, right? So what you're talking about is a parallel program, and we'll see how that, we'll add notion of threads in the next lecture, right? But for now, the fundamental architecture that all these machines operate on assume that you are working on a sequential set of instructions, right? So if you say, I want a mouse, I want a keyboard, there's no way for you to say, I want both these simultaneously, right? You have to do one at a time. So you have to ask for a mouse. Until you get the mouse, you can't ask for the keyboard, right? And parallel programs can kind of make this, relax it, but they also add more complications. So for now, you can't do that, right? So you can't be on both two queues, right? If you're on two queues, then that's bad, right? Because it assumes that you're only in one queue. So if you happen to be on the ready queue and this queue at the same time, right? So they are managed differently. So when the OS comes in and it needs something to run, it looks in the ready queue and it'll run it, right? You can't be ready to run and simultaneously waiting for I/O, right? So yeah, that's so you have lots of these queues and the PCB gets moved around, and essentially you're just moving the pointer, so it's not so bad. You don't move the whole structure, right? But each structure can be potentially large, right? So the long-term scheduler, part of the quiz was it is trying to figure out if you keep adding processes at free will, right? eventually you can come to a point where there are so many PCBs, right, that you have this long queues. Your ready queue is like 200 processes, and your all memory is being allocated and all those things. Your machine eventually dies, right? I'm playing this game where if there are two, I can say you go kind of stuff, right? But if I have say 1,000 processes, right, then I can say the first one, second one, third one, fourth one, each one of you go for 1 millisecond, right? By the time I'm done with the 1,000th one and I go back to the first one, right, essentially you get so little of the CPU that the machine is useless, right? You get 1,000th of the machine or whatever, and that's not useful at all, right? So at some point it has to say, I know I can do 1,000 processes, but no, I'm not going to do that, right? I'm going to kick you off because that's a long-term scheduler. It says I can deal with 1,000, but realistically I can't, right? So I have to look in the long term and say, you're not coming in. So if you want to send one more process, you have to wait. And that's the notion of the long-term scheduler, right? Nothing to do with when you start it or whatever, it's always running, right? And since it doesn't have to be doing the micromanagement, it can be accurate, it can run when it's idle, and it can make some good heuristics, right? You don't want to be too afraid to take in new processes, but you have to make a good choice, right? The short-term scheduler is the one which figures out when you move from ready to running state, right? And that has to run often, and the often depends on the hertz value you're going to set on the homework project 1, right? So if you set 1,000 hertz, that means every second, 1,000 times, you're going to make the decision, right? So when you make the decision, you better be fast, because if it take you 1 millisecond to make the decision, you're not making anything at all. Every 1,000th of a second, you're deciding for 1,000th of a second, right? So you're practically deciding what to do, right? So you want the short-term scheduler to be really quick, really fast. Just make the best you think it can do, and let it go, right? So that's one of the main differences. The short-term scheduler does not think about anything. If it sees something on the ready queue, it puts it on the run queue, right? And it wants to do it fast and then make progress. Long-term scheduler decides this stuff. There's also a notion of medium-term scheduler where it can come in, and if it sees too many processes, it can put some of them to sleep by putting them on the disk, right? And we'll see them later on what that means, right? So there are two notions of what processes do, and real processes can be in the middle, right? There's a notion of a IO-bound processor, and there's a notion of a CPU-bound processor. So if you wrote a program called int I, for j equals 1 to million, right? Compute prime number or something, right? And this is a CPU-bound job because it's probably not doing any I/O. It's just doing computation. So if you throw more CPU at it, it's happy, right? If you give all the CPU, it can keep using it because it's just going through. So it's always in the ready state and the run state, right? It never goes to the disk state. Whereas IO-bound job is something like a word processor, right? Every time you press a key, some input goes, your word does something, it formats or whatever, and then it comes and waits for you to type more stuff, right? So those are IO-bound jobs and CPU-bound jobs, and real jobs go through different phases. If you go to Word and then you say format or spell check or something, it goes through some CPU process, right? So the mix of what these are and what is important to you is the deciding factor for your schedulers, right? So a machine can decide CPU-bound jobs are good, or it can decide IO-bound jobs are good, right? So for a desktop machine, which one would you prefer, IO-bound job or a CPU-bound job? Yeah.
IO.
Why?
You use a lot of programs like Microsoft Word or Photoshop or Maya that wait for user input before doing computations.
Yeah, so it's not rocket science because it sounds about right? I mean, it doesn't have to be a reason why you do that. So most of the OS is designed like that. People say, well, let's try that and see how it goes. And if it turns out to be bad, it's not good, right? So what happens if you just keep doing the mouse? How many of you, when you're the machine is not doing very fast, do this, keep moving the mouse like that, right? It's like when you, on the elevator, people keep pressing the button as if that's going to speed up your elevator, right? You guys seen it, right? I mean, the elevator, if you want to see it, go to the debarked elevator, right? And that's excruciatingly slow going up. But many people are like, busy typing it, right? So how many of you tried the same with the mouse or keyboard, right? So is that a good idea, do you think? Because the OS is it's assuming that any input I/O would be good. I mean, if you're doing Maya, that's an excellent thing. But if you're just moving a mouse like that, it's already busy, it's already doing something, but it's programmed to deal with you first. It's programmed to deal with your mouse movements first before it goes on to do something else, right? Has one of you had a chance to work on mainframe computers? There are fewer of them these days, right? But essentially, mainframes operate on the CPU-bound task because they're very expensive. You pay a few $1 million to buy these machines, and you're not supposed to be interacting with them. You're not supposed to be talking to them or whatever. So they don't care about interactive jobs, right? In fact, most of them collect a whole screen full of information, and then you send it off, right? And you get the results back. So if you work on that model, you won't get into this trouble. But in a normal machine, if your machine is slow, do not move your mouse because you are making stuff worse, right? It may feel good, but not the right thing to do, right? So two of the important operations when you have a process, the OS kind of keeps moving stuff around, right? The two other important things that operations you do on a process is process creation and process termination, right? Process creation is when you first start the program, what happens, and process termination is when you do exit, right? So there are two ways to exit the program, which is either through exit, right? In your C program, you call exit some value, right? Or you can call abort, right? If you do a illegal memory access or something, you program, the OS kills you, right? It aborts you whether you choose to or not, right? So those are the two main operations you want to know, right? So let's look at the first notion of process creation, right? The way process creation is handled in something like Unix or Windows and stuff is a process creation has to be done by another process, right? You can't magically start a process. There has to be a process which starts another process, right? So it's always a hierarchical stuff. There is process 0, which magically gets started. Everything else starts from there, right? So if you want to start Microsoft Word, you have to be running something else which starts Microsoft Word, right? The way you create a process is through a process called forking, right? Essentially, let's assume you have a process here, right, with all the stacks and heaps and all those things, right? When you call something like a fork, it creates an exact copy of this here, right? And later on in the course, we'll see how this can be optimized. But essentially, functionally, you create an exact copy, right? And both of them at this after the fork, both of them run, right? Both of them are new processes. Both of them have their own PCBs, and both of them are running the exact same code, right? And it's not very interesting to run two programs doing the exact same thing. So you have the notion of exec, right? Exec says load a new program. So you fork yourself, and then one of them decides to load a new program onto itself, right? And that's the fork and exec model, right? So here's a simple example of how these things happen, right? So essentially this, so the only difference is the fork system call returns the child's process ID, the ID that the program can deal with, to the parent, right? The parent gets 0 because it's not the child, it's a parent. The child will, the parent will get the process ID of the child. The child will get a 0, right? So essentially, if you do a fork, right, and the second sentence is fork, right? If the process ID is less than 0, that's some error happened, and you return something, right? Else, if the process ID is 0, that means the child's process ID is what is returned, and if you're the child, so you get a 0, right? Then the child gets to exec this call and run something, which essentially replaces. So this is let's say this is the parent, and this is the child, right? You replace the child with the ls value, and you proceed, right? The parent can issue a call called wait. which says I'll wait for the child to finish, and once it finishes, I'll complete, right? If you didn't do the exec, both of them are running at the same time. Both of them are known to the OS at the same time, right? You make an exact copy, right? Which means that some of the things you share, some of them you don't share, right? Some of them you share. Anything you are using from outside, now you get to do the sharing because they are pointing to something else, right? Whereas if they are local to you, you no longer share. So if you had a PID, right? In both of them get a copy of PID with the value of what it was before it forked, right? So from that point on, those values are not shared. But if it is opening a file, doing something on the outside, it can mess with both of them, right? For the most part, you don't worry about that because the first thing you do is exec and fork and exec, you replace the whole thing and you proceed, right? So that's the way you create a new process. You clone yourself and then you start a new process, right? And we'll talk about what it means for the process to communicate with each other on the next lecture.